Good afternoon, everyone. We now have the pleasure of welcoming Dr. Panthadeep Bhattacharjee, sir, our expected academician in the field of computer science and engineering. Sir's main area of work include data mining, machine learning, pattern recognition, and intelligent algorithms. He has received recognition for his excellent research, including a Best Thesis Award at an international conference. Before joining NIT Rourkela, he has served at reputed institutions such as IIIT Guwahati and KIT University. He is also a professional member of ACM and is actively involved in guiding students in research and innovation. It's an honor to have him with us today. May I kindly request Sir to take the stage and share his valuable session with us. Sir, please.
Yeah, thanks everybody. First of all, I would like to express my heartfelt thanks and gratitude to the organizers of BPUT. So I received a, you can say, call from our HOD sir, Professor Vibhudatta Sahu, and a couple of days back he said that we have a talk at BPUT. So we're pretty excited to come here. It's a very reputed university in the state of Odisha and nationally as well. And I think you have got a fair enough introduction. So before we start with today's talk, I would like to say that based on my convenience and for understanding of our dear colleagues and faculty members, I not only navigate through these slides just for the sake of reading, but I try to get into the inner details of how we work basically, especially the core machine learning algorithms. So prior to that, you must have seen Professor Anup come here, Professor Prasanjit as well, and Professor Shivram, and of course Professor Sahu sir as well. So more related into the AI part. So today what we'll do is that I'll probably sit here. We have a lot of informal scribblings I will actually do, just not read through the slides. Probably that will help you to understand more what is the inner working mechanism. So some of the basic conventional ML algorithms, KNN is extremely foundational method basically. And please let me know if I'm going too fast. I can actually adjust the pace basically. So KNN is one of them. The second that we'll be looking at is your dimensionality reduction, actually. And there is one more aspect, I think, your bias classification as well, the bias classifier. So out of the three primary topics that we'll discuss today, two of them are algorithms and one is basically a tool or a essential technique, actually. So KNN and bias classification, these are nothing but, you can say, very, very foundational classifier ML models. And dimensionality reduction is something very interesting because if you look at the space that we are actually sitting here, it's a 3D space basically, something which is within our visual range. Anything that goes beyond, we won't be able to visualize. We are not actually capable to do it. Anything which is less, we can still visualize. For example, if we look at this table, just this top surface of this table, it's a 2D surface basically. It's still within our visual range. If you look at this room, it's a 3D structure, it's still within our visual range. But beyond that, it's not in our visual range. So ever wondered the plots that we do in all the machine learning algorithms, the plots that we do, the clustering plot, be it in MATLAB or Python or any language, the plots that you do, it's not that the points are actually 3D. The points can be 4D, 5D, 10D, trimmed to a certain dimension. Trimmed means we are actually cutting the number of dimensions. But then again, we can't really abruptly reduce the dimensions all of a sudden. If the number of dimensions are say 40, for example, suppose I am a 40 dimensional attribute. I hope my explanations are audible towards the back. I hope everybody is understanding. If you have slightest of doubts, please do feel to interrupt. I'll try my best to explain. So for example, say I am a 40D attribute. I'll come to the slides. The time is about to start. Now, I can't really visualize myself in a 40D because our world actually is not a 40D space. It's a 3D space, basically. Now, how do I cut the dimensions? So there are certain techniques out of which we are going to discuss one particular technique today. It's called the principal component analysis. So a prerequisite could have been better, but I'll try to navigate my explanation in such a way so that everybody understands. actually. So quite a bit of maths is involved. So when we talk about ML at the undergraduate level, we look at the codes or some basic understanding. But if you go at the higher level, it's more about the maths and probability and vector algebra, and that is actually simulated through your codes. I mean, that's the fundamental explanation basically. You go to any top universities, be it ISC Bangalore or IITs or ISRS or NITs even, most of the profs will tell you two things. You got to have very strong foundation about probability and statistics, your linear algebra, your optimization, and then you start your conventional ML methods, actually. So that's the prerequisite, basically. Or else you will see the notations, they will keep coming, and mostly you will find it very difficult to understand. So that's why in today's talk, I'll try to mix both those things. Of course, in 2 hours time, it might not be possible to touch in each and everything. So 2 classic ML algorithms and a demonstrative reduction technique, basically. Okay. So shall I explain from here, or no, I need to do some explanation also in the, okay, fine. Fair enough. I have to show something through explanations. I hope you don't mind me sitting and explaining. Yeah, fine, fair enough. Thank you. Okay, so let us start now. If I have this, okay. So you can see the topic itself is K nearest neighbor learning. So before we, as I said, I mean, it won't be a just navigation of slides. I hope people get something out of it. Now, there are a couple of things in this title itself. One is nearest and the other is learning, basically. Neighbor, everybody knows what is a neighbor. You know, our proximity, you know, something which is very close to us. But there's a very interesting term called K nearest. So what is K nearest? K nearest means that if I talk about a, so I'll of course go into the technical part of it, but suppose I talk about a certain object here. For example, this empty table right at the front. So what are its nearest, basically? Maybe the table here, maybe the table here, the table here, and that's all about it. But who has said that there are only 3 tables which are the nearest, basically? There can be a number of tables as well. That actually depends on the value of this hyperparameter called K. Now, what is a hyperparameter? What's the difference between a hyperparameter and a parameter? You must have heard this term many a time in your simulation of the ML algorithms, hyperparameter or parameter. Hyperparameters are something which we give externally to an algorithm. Say in your training of the ML model, you must have seen there are 3 phases. One is the training phase, the next is the validation phase, and the third is the testing phase. Right? The train data, the test data, and in between have the validation phase. So in the training phase, we train the entire model, and whatever we get, the parameters are tuned basically, but they are learned from the model itself. When we go to the validation phase, that's not training. There we externally keep on changing the parameters to the trained model to see if it is closing to the results or not, ground truth or not. Those are called the hyperparameters. So in the layman's term, any argument or anything which is externally provided to a model, which is not learned from the model itself, but it depends on the external tuning, they are called hyperparameters. And the stuffs which are actually learned from the model itself in course of training, they are called parameters, basically. So K is one such hyperparameter here because it's human fixed. We are giving it. Actually, we are testing it, not that the model is giving to us. And what is learning here? You know, the learning means as we go through the course of the training process, it's getting something. It's receiving some, say, internal coefficients or internal weights that it is learning in course of its like execution. So that's how we start with our, you can say, first algorithm, which is called K nearest neighbor or KNN, actually. So what do we expect here is called the fundamental task is the task of the classification. So what is classification? It's just an allocation kind of. Suppose there are 2 buckets and you are going to put 2 different entities into 2 buckets, given that what is the property of a certain entity. For example, say there are people who are teaching senior courses and there are people who are teaching, say, primary level courses. Thank you. Yeah, so again, just to reiterate, I take the liberty of sitting because of this explanation, or else I can stand here and explain. And I would probably like to, that's how I teach my students as well, because this understanding, I believe it will benefit you a lot more rather than just navigating through these slides, okay? So I have my tools here, so I need to access them from this place itself. I hope that's okay with everybody. Okay, thank you. Okay, so okay, so what is classification? Now, there are two things. Okay, now there are two things. The first thing is that before we start with this entire KNN thing, in case a lot of you might be knowing this as well, one is your classification, the other is your regression, basically. Regression you must have heard, logistic regression, linear regression. But what's the fundamental difference, basically? These are two different things, basically. They are not the same. So when we talk about classification, like I said a couple of minutes ago, in a very, very simple term, it's an allocator. For example, say there are 20 faculties sitting out here. Some of them are only guiding students. Some of them are only teaching students. Just for example, some of them are only focused on R&D, research. Their primary job is to do the research. And some of them are only focused on teaching the students. Let's say there are two classes now. Now, a classification, what it says is that, what I will do is that, so suppose I am an ML model, I am an algorithm, I will take an unknown data. For example, I will invite any faculty to me and he or she has his own properties. Now, it's my job to allocate whether you are going to teach students or you are going to do research. Whether you are going for class 1 or you are going for class 2. That's called classification. But what is regression? Regression means I will invite you, I will judge you based on your parameter, but I will stop there itself. Whatever your capabilities are, whatever your IQ level is, whatever your degrees are, whatever your credit points and API scores and etc., you will stop there. You are not going to get allocated anywhere. That's called regression. So the linear regression, the algorithm that we, I think it's the first algorithm that we study in any ML course. What do you see? Prediction of stock prices. What is the amount of rainfall that we'll have tomorrow? What are the chances that India wins today's match? So aren't these real numbers? They are not allocators basically, they are just real numbers. What is the probability that tomorrow there will be a rain? So suppose, what is the probability that today, say India will win the match? What is the probability that you will stay in this campus for till the time of retirement? Or any sort of real number basically. So any number which you are talking about in the real space, minus infinity to plus infinity, it's called a regression. It's just a simple conclusion of an answer basically. Just a simple answer, it's an answer. So you have a function. So if I say a regression problem, I'll come to KNN. If I say a regression problem, so given a function f, your input will be a d-dimensional input and your output will be your r. And r belongs to r is any real number, 2.1, 3.1, 0.5, 0.7, anything. This is called regression. Okay. Just pardon me, I'm writing with my mouse pad, so just ignore the handwriting. I hope if it's understandable, that's enough for me. Now, what is classification? What classification says is, you have a function f, and you are actually giving an input rd, which is a d-dimensional element, and your results are not absolute numbers, but they are now classes, basically. Say C1, C2, and so on, if it's a multi-class problem. So like I said in our explanation just a while ago, if I say it's a two-class problem, that one section is going to do the research, the other section is going to teach the students, then it becomes a binary classification. It's a two-class classification. If I say that one section is going to only guide the students, other section is only going to take PG students, other section of faculty is only going to teach the UG students, it's a three-class problem. So what I will do is that, maybe I will invite you, maybe I will look at your parameters, your scores, your degrees and all of that, but that's not all about it. I'll actually allocate you to one of those three buckets. That is called classification. But if I stop there to your final value, that is called regression. I hope that's clear with everybody. I hope if you have any questions, maybe I can take it later on, basically. Okay. Now what KNN does is that it does the classification job. So there are quite a few mathematics involved here. Of course, it will be a bit overwhelming for us to understand the maths. So that's why I'll try to project my explanation in such a way so that everybody is able to have a grasp of it, basically. I mean, if you want the slides, you will see it's the same thing that I'm actually speaking here now. So what's the task? So given a test example X, given a data point, find the training set examples x1 a1 till xk yk that are closest to x, right? So what it is trying to say here? So let me just explain it once again. If I say a certain point x, just don't think it as a discrete entity. It's a vector now. It's a vector. It's a multi-dimensional vector. We are not anymore. We are not in this discrete space. We are just not talking about 1, 2, 3, 4. When you talk about machine learning, any object, any entity, any item is a multi-dimensional entity. For example, if I talk myself about a data point, then my entities will be my height, my weight, my BMI, my credentials, my around the passport number, etc., which is encoded basically. Which is encoded. I hope I'm clear with everybody. So that will help us to understand the rest of the slides as well. Whenever I talk about a certain data point X, you just mean to say that it's a vector. It's a vector of say 5 dimensions, 7 dimensions, 8 dimensions, just a multi-attribute vector. Simple as that. Right? There's no discrete space we are not talking about. Fine. So when I talk about this value called X, this entity called X, this means it's a vector of multi-dimensions. So this is, say, these are my dimensions, for example. Right? Say, its value can be any real number, say 2.1, 3.1, minus 7.9, anything from minus infinity to plus infinity, basically. So any point, see all these points. So this is such a simple graph. So it's a 2D space, right? So everything will be an XY coordinate. So we can say it's a two attribute item. So we are 3 attributes item. But in general, what we do is that we define each of them as a multi-attribute item. Fine, fair enough, right? So, yeah. So now what KNN tries to say is that, I bring an arbitrary point here. It's an unknown point. And I compute the distances with all the other points in the data space. The training will come sometime later. Let me just start with the KNN here. I bring an unknown point in the data space. I hope the screen is visible to everybody. I bring an unknown point and my final job is to classify. That means it's a classification problem. Just a while ago, I told what's the difference between classification and regression. Classification is just an allocator. It's a bucket allocator, basically. You bring an unknown point, take its properties, and decide that what allocation it's going to happen. Regression is just a real number conclusion. Take an unknown point, whatever the final answer is, you stop there. That is called regression. So here we are discussing KNN in context of your classification. So take an unknown point, and with all the other points in the data space, you find the Euclidean distance. I think Euclidean distance is more or less known to all of us. But any distance you can take. You can take the Manhattan's distance, you can take the Minkowski's distance, you can take Euclidean is very common, but let us take Euclidean distance for the time being. So now what happens? So what happens is this. So this is a certain point, and what I do is I compute the Euclidean distances with all the other points in the data space. Mind you, this is itself a multi-dimensional point. In this case, it's a 2-dimensional, but let us say in general case, it's a multi-dimensional point. So I compute the distances with all the points. So distance with this, 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 and all the other points basically. Then what I do is that I write those distances individually. Say D1, D2, D3, and till you can say Dn minus 1. Why Dn minus 1? Because the self point itself, distance to distance, it doesn't make any sense actually. So apart from itself, apart from this point, I actually try to find the distances with all the other points in the data space, right? And I actually store these distances in a certain vector, in a certain storage space, right? Next, what I do is, I now sort this distance in an increasing order, right? If I sort the distances in an increasing order, can we not say that these points are relatively closer to this unknown point? Unknown means it has just newly come to the data space. Why I call it unknown is that its class is not known. These points, they are already classified. You can say green class, blue class, red class, etc., etc. But this point is yet to be classified. It's a classification problem, but this point is yet to be classified. So when I bring this new point here, I compute the distances with all of them, all the other points, and I store their individual separation or individual distances in a certain space. And then next what I do, I sort these distances in an increasing order. So which are my closer points? Supposedly these are my closer points. And as we go further, these are my distant points. So generally these di's or di plus 1 or di plus 2, they will be more as compared to these distances. But initially, do you have any way of knowing this? We don't. Because we don't know in what index the points are actually computed, the distances are computed. We take a certain point, certain unknown point x, we blankly compute the distances. For example, if I'm an unknown point, I'm going to classify myself, I'll compute the distances with all the colleagues and faculty members sitting out here. So initially, I don't have any idea who is closer to me and who is farther from me, and it's purely an Euclidean distance. So perhaps I can say maybe the colleagues who are sitting here, they're relatively closer to me. Maybe the colleagues who are sitting towards the end, they are farther from me. I hope that's clear. This concept is clear. Fine. Now what we do is that this term called k actually comes into the picture. So how many you are going to accommodate? How many you are going to accommodate? In case you are seeing this circle, this means how many top k closest you are going to take by the side of you. I can't take all the people around me. How many top k you are going to take? So there are issues here as well. People would say that if I take only one NN, so I accept only one person as my closest, and the other extreme case is that I accept everybody as my closest. It's a logical assumption. I hope I've made the sense clear, basically. This is about top k nearest. The title itself says top k nearest. That means take an unknown point. Your job is to classify it. Initially you find the distances with all other points in the data space and then sort these distances in increasing order. So once you sort these distances in increasing order, you find who are closer to you and who are further from you. Fine. But how many people you are going to take as your neighbor? If I say that I have 5NN, I am a 5NN classifier. Instead of the value of k, I put the value of k as 5. Suppose it's a 5NN classifier. Then I can say maybe the faculties or the colleagues, esteemed colleagues who are sitting out here, they will be a part of my top k nearest neighbors. If I say 7NN, maybe I will say the dear friends or colleagues who are sitting out here, 5 plus 2, 7. If I go for 10NN, then maybe this entire bunch will cover up this initial first row. Right? If I go for even more, then maybe few of my colleagues who are sitting out towards the end, they will also come within my neighborhood. So this discussion will reserve it later on, but let us say that we pick a certain reasonable A and it's going to be an odd number. It's going to be an odd number and I'll tell you why. So now what happens is, I'll come to this later on. So now what happens is, suppose this unknown point, it has decided 5 points as its top 5 nearest neighbor. 1, 2, 3, 4, 5. Right. Now, amongst these 5 points, or if you are seeing here, so suppose this unknown point, it has said these few points as its top k nearest neighbors. This few. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say 10 NN or say 11 NN, for example. Any doubts still now? I think it's more or less apparent to everybody. Now, amongst these 10 or 11 points, you got to see which is the dominant class here. Which is the dominant class? For example, out of these 11 points, we can see that 1, 2, 3, 4, 5, 6, 7, 7 are from class blue. And probably rest 4 of them are from class green. Quite obvious. Quite obvious. Suppose I have decided, it's an arbitrary selection, that I go for 11NN. I can go for 5NN as well. If I go for 5NN, my circle will be lesser. My range will be less. If I go for 11NN, my range is this much. If I go for even further, my range increases even further, basically. Suppose I go for 11NN. So in this place, what we see is that 7 of them are from class blue and 4 of them are from class green, actually. So which is the dominating class? It's the blue class. Quite obvious. Blue class is the most dominating. And red class has probably one element here. So if I now divide into classes of the neighbors here, these 11 neighbors, I'll say that 7 of them are from, you can say blue class, maybe 3 or 4 of them are from green class, and there's just a solitary element which is from your red class. So the proportion is now maybe you can say 7:4:1. So what is my dominating class? It's blue. Now the theory says is that, my algorithm says is that this unknown element, its class was not known previously, but after this computation, its class becomes blue. Why? Because its KNN is dominated by the class blue. It's just to say in this way, say if I am to classify myself, and I have taken a few colleagues from here, few colleagues from here, and few colleagues from here, now I'll see that which properties are dominated by how many of them. The property which most number of people dominate, that will become my property. Is that clear, everybody? Pretty obvious. I can't be more simpler than this. Pretty obvious. But what is the ground truth? Do we know that it's actually blue class? So in machine learning, there are two things. One is the ground truth and one is what the model gives. One is what your model or your equation or your formulation gives, and one is what the experiments are giving you. I hope these two things should be distinguished very clearly. One is what the experiment is giving you or the raw data set is giving you, and one is what your model is giving you. Now, if the ground truth of this element, because for us it's unknown, but once we know this, we can compare to what it was actually initially. So in case when you test a model, I think you have heard about this testing phase, right? Most of training phase, testing phase. What is testing phase basically? What is testing phase? Testing phase means that once you have trained your model sufficiently well, you get a result. For a given input, you get a certain output. Now, is that the output what your actual story is? That's where the accuracy thing comes into the picture. Or else, how do you find the accuracy? For finding an accuracy, you need to compare with something which is already a known thing, right? Which is already an established thing. So if I say that this belongs to class blue, is it actually class blue before being coming to this algorithm? That we have to find out. Was it actually blue? It might be red as well, right? It might be red as well. Only after classification by this, say 11NN classification model, it has gone to be class blue. But is it actually blue or red? That has to be verified from its ground truth. So this is the story with every odd unknown element which comes here. Suppose a new unknown element comes here, I find the same 11NN or say 5NN. How do I find it? I compute the distances. I store the distances in a certain storage, and I sort them in increasing order. The ones which are closer to me, they will become my closest neighbors. Now I will say what are my existing classes. Say 3 or 4 classes are there. Say here 3 classes are there. The red class, the green class, as well as the blue class. Now amongst my neighbor, how many people are satisfying which class? If a certain class is dominated by most number of people, that will become my class. It's as simple as that. I hope that's clear to one. Right? There are no ambiguities as such. But is it actually my class? This is what the model is giving. This is what the mathematical abstract is giving. This is what the classifier is giving. But what is my ground truth? Am I actually a green class or a blue class individual or a red class individual? And now say somebody else comes to this room again and again puts himself to that model, some classification will happen. Again 5NN will happen. Again 5 people will come closer to him. Then the properties which is dominated by most number of people, that will become his class. But is it actually his class? That we have to verify from the ground truth. And that's where the accuracy thing comes into the picture. So if you find out for 10 unknown individuals, red, 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 blue, 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 and say green, green. So suppose I say all the reds were actually red, all the blues were actually blue, But the two people who were identified as green, they were actually reds. What is the accuracy? 80%. Am I able to explain this? What's the accuracy? Because two people missed out. The model gave them as red, but actually they were blue. That's what we do in the testing phase. Right? Have I been able to explain? So can we move forward? Fine. Thank you. Okay, so now we gradually go into the complexity of this entire topic. Like I said, by and large things are very mathematical sort of. If we devote 1 or 2 hours in complex mathematics, it doesn't serve any purpose. So it's my duty to explain it in as layman's term as possible, as abstract way as possible, so that everybody is able to understand what things are all about, basically. So this is the story with every unknown point. Even if you look at this unknown point, this one, suppose I am to classify it, you see your visual estimation says that it's highly green dominated neighborhood, right? That means it has also calculated its 11NN kind of a thing. Why 11NN? You can take 5NN also, 7NN, 9NN, but take odd numbers. What numbers? Why? Because if you take even numbers, unfortunately, if you have equal number of classes existing, it will be very difficult for you to classify. I hope you understand this. Suppose I take a 8NN kind of a thing. I have 4 red class and 4 blue class. So which class I am going to be? It's a confusion, sort of. Then there will be an arbitrary choice. And then again, there are chances of misclassification. So suppose, 8NN or say 6NN, for example. 3 of blue class, 3 of red class. And I say that, look, I'll be a blue class, but actually I was red. Here you missed one. You are not able to judge. So that's why please take odd numbers when you go for KNN classification. So eventually you have at least one which will dominate, basically. Right? Fair enough? So even for this, you see in your visual estimation, this is highly a green dominated neighborhood. That means maybe you can say 10 or 11 NN it can accommodate. So 10 or 11 means, suppose if we magnify this entire space, you have 10 number of or 11 number of neighborhood accommodation, and you see it's heavily green dominated. It's basically a, disproportional dominance actually. So you can say 10:1. 1 blue class and 10 of them are green class. So this is a no-brainer basically. It's pretty obvious that this unknown point will go to a green class. Fine, quite obvious, but is it actually green class? That's the thing. It might be, it might not be. It might be, it might not be, but the model itself says is that it's a green class, right? So there are many things to explain. I hope I complete within a passage of time. I would have liked to discuss about the accuracy also, because discussing KNN is fine, but accuracy is a big thing here. That itself is a different chapter in machine learning. Whatever accuracy that I'm telling, just match the correct or match the wrong ones. That's a very simple, vague judgment of accuracy. There are too many other parameters which are there, the F1 score, the precision, the recall, and etc., which probably would have taken a separate, lecture altogether. But let us see, this is the broad idea about KNN, and I think now everybody will be able to relate what we are going to discuss actually. Rather than discussing this, complex maths or, too many notations, probably it's fair enough to give an overall idea what things are all about. So to train to save the data, it's very fast. You might build some indices and find the K training set examples, x1, y1 till xk, yk that are closest to x. And I've already explained what do you mean by closest to x. Take a certain element, find the Euclidean distances, sort them out in increasing order, take the first 5 closest or first 7 closest. That's the simple meaning of closest, basically, right? And predict the most frequent level in that set. So everything that I've explained in the previous slide, you will be very easily able to relate what do you mean by predict the most frequent level in the set. What is most frequent level? Say I take 11 and then 7 people are red, 4 people, say 3 people are green and 1 person is red. So what's the most frequent? It's the, say, red, right? Or say blue. In our case, it was blue. Or say green, whichever. The fundamental idea is that the class which is dominated by most number of people. That's it. That's the most frequent level. And your class will be that dominating class itself. But is it the actual class? There is no guarantee. Fine? I hope there are no doubts as such now. Prediction is relatively slow compared to a linear classifier or decision tree. Now, why? The big question is why? So, I'm not going to ask questions because everybody is a faculty here, but I'll probably tell the answer myself. The reason is that eventually what happens is, let us say this single point, currently what we are discussing is that I have discussed about KNN, I have discussed about the dominating frequencies, I have discussed about the classes, I have discussed about regression. But now we are going to discuss about the performance of this model, and it is slow. Slow. The word is slow. Why? Strictly, we have mentioned that it is not fast. It is not fast because if you compute the distances with all the other points, say n-1 number of points, minimum, that many number of comparisons you require. Tomorrow, if I increase my number of data points, say 100 more points have joined, what it will be? n-1 plus 100. Tomorrow, again 100 more points have joined, n-1 plus 200. Tomorrow, again k number of points have joined, n-1 plus 200 plus k. So effectively what is happening is that for a bigger data set, when we talk about an ML model, we don't deal in terms of thousands. We deal in terms of millions at least. Because of the, say, I work in graphs, I work in graph-based machine learning. In our case, it's a very, very torrid situation. We have to deal in terms of millions. But because of lack of compute power, in most of the institutes, we don't have that leverage to run the bigger graphs. Why? Because when you talk about graphs, you talk about order of n square complexity. From the basic algorithm concept, order of n square, those who are from computer science will be able to understand. We talk about order of n square complexity. You need a basic matrix you need to store the graph. That means minimum n square number of cells. And your game is all over. Because the more you increase the number of data points, this n square actually increases disproportionately, and the RAM present in your system, it's not able to accommodate. And that's the problem that we face in this kind of models. Because it's completely based on computation of distances, as you increase it, you just compute it. n-1 plus n-1 plus k plus n-1 plus 2k plus n-1 plus 3k plus n-1 plus 4k. So you are adding n. And when that n is close to m, you are again touching n square. I hope I've been able to make some sense. n-1 plus n-2 plus n-3 plus n. Suppose you have 1 increase in this base data set. n-1 plus n-2 plus n-3. When this data set keeps on increasing to a higher volume, it gradually turns out to be from linear to quadratic time complexity. And anything which is quadratic, it's definitely not an efficient algorithm. And that's why it's a very, very slow method to start with. Yes, it has its advantages. It's a simple method relatively, but it has its disadvantages as well because of the slowness. Fine, fair enough. Can we move ahead? Okay. Yeah, very good question. So, very, very good question. Fantastic. We decide k value by an empirical process. That means it's a fantastic question. The value of k is decided by two things. I was going to discuss it just now, but because you have brought up this question, I will discuss it now itself. We start with a certain value of k arbitrarily, and we judge what is the degree of smoothness of class separation. Now, imagine we start with a value of k equal to 1. Just try to imagine this situation before I go back to the presentation. What will be k equal to 1? So 1 NN situation. Only one people I can accommodate as my neighbor. Does it make sense? Only one person, right? That means who is closest to me, the most closest. Maybe sir is most closest. So in my proximity, in my neighborhood area, only sir will be there, nobody else. What will be my situation in that case? Because just 5 minutes ago I told you have 10 people, 7 are blue class, 2 are green class, 1 is red class, which is the most dominating. Blue is most dominating, so I'll be blue. But here I don't have any choice as such, right? Whatever his class is, that will be my class. I hope I'm able to make sense. Whatever his class will be, I am left for no choice at all, because I don't have the second person to compare. I don't have the third person to compare. I don't have the fourth or fifth person to compare. If he is class red, then I have to be class red, because he's just the one accommodator, right? Am I able to explain, please? Or else you can raise your questions. If I have 11 NN case, say 11 nearest neighbors are there, 7 are blue, 3 are red, 1 is green. Which is the most dominating? Blue is most dominating. So my class is also blue. That's what I told just a while ago. But if I have a 1 NN case, what's the situation? There is no comparison as such. I'm not in a position to compare because I'm only accommodating one person as my nearest neighbor. So whatever his class is, it's a 1-0 kind of a situation. His class will be my class. And that will be for 10 other unknown individuals who will be coming here to classify themselves. Just a few minutes ago when I said that if you bring 10 unknown data points and you put in this KNN model to classify themselves, they'll be taking help of this algorithm. And say that every point will compute its 11 NN, see which is the most dominant class amongst his neighbors, that will be his class. Now the same situation you put and say that it's a 1 NN case now. It's a 1 NN. Coming to your question, I'll make it 2 NN, I'll make it 3 NN, I'll make it 5 NN also. If it's a 1 NN case, what will happen is that my class boundary will be very, very ragged. I need a smoother class boundary. Whoever teaches, whoever does research. Whoever teaches UG, whoever teaches PG, whoever does research. I need a very, very smooth class boundary. If I have a 1 NN case, my smoothness will be very hampered. It will be very ragged. It will be an overfitting kind of a case. Have you heard about overfitting? I think, at least I expect. Anybody? Yes, pardon? Yeah, you have heard about overfitting. So what is overfitting? That means you are living in an impression that it's a very, very correct classification case for your training data. I'm not trying to be too technical, but overfitting means your training error is very less. It's as less as possible. But when your unknown data comes, you are getting it completely wrong. You are living in an illusion that your model performs very well. In your training set, you are trained with such efficiency that your model is almost showing 100% accuracy, 95 to 100%. But the moment you go to the testing phase, it gets horribly disrupted. That's called overfitting. That means you are fitting everything. In your domain, you are fitting everything initially. But when the unknown samples come, because you have taken such a low size data set, you are not able to respond to the unknown test samples. So when you have a 1 NN situation, we suffer from the problem of overfitting. You are thinking that you have actually given the correct classification, but the class boundaries are very ragged. So this case is actually discussed here. This is a 1 NN situation. You see the class boundaries are very ragged, very disruptive class boundaries. But if you have larger NN, so when K is, say, significantly large, say K is greater than 1, then for a certain point P, you are actually accommodating a lot more number of points here. That means when your K is large, you have this kind of a situation. So you have a broader circle, a broader region basically. When your K is small, you have a relatively smaller region. I hope everybody is able to understand. So when your K is large, what happens is that you have a choice. Am I right? When your K is large, that means more people are actually getting into a neighborhood. More number of people are understanding your or getting in proximity of your neighborhood. You have a choice to decide that yes, there are 15 people are there, 7 are blue, 3 are red, so some are green, some are yellow, which is the most dominating, I'll be of that class. That still makes some sense. But when it's 1, it doesn't make any sense because it's disproportionately skewed. You have just one choice and that also you don't know whether it's correct or wrong. So now you go to 2 NN. Again, there is a problem, it's an even number. Then you go to 3 NN. You go to 4 NN, you go to 5 NN. And every time you see at which NN that class separation smoothness is coming, you got to smoothen it. That means your separation of the classes should be somewhat linear, a straight line kind of a thing. That UG teacher, PG teacher, research teacher. Clear division should be there. Not ragged kind of a thing. That some are UG, some are PG, some are research. Ragged classification is very difficult to handle. So the place where you get very smooth distinction between the classes, that's where you stop and say that, look, I have found my K. I hope I've answered your question. At every K size, you are going to find out the degree of smoothness of the class separation. The value of K for which you find the degree of smoothness to be very, very perfect or maybe near perfect, that you are able to distinguish somewhat, you say that, look, I will stop here. That will be my K. For all the upcoming data also. It's a very good question. Fantastic question. Absolutely. Elbow is for K-means. Elbow is for K-means. Where you have ICW, I mean intra-cluster, some score is there basically. Intra-cluster connecting score is there, ICWS, where at every point you find the ICWS score. and the moment you have the inflection, you stop there. Very good question. Fantastic. So here what we do is that we find the degree of smoothness. The elbow method is for K-means, actually. That I think those who have seen, it's a very age-old clustering algorithm. Maybe tomorrow we'll discuss it. So this is a classic case of the 1NN decision boundary. So this is a classic case of KNN, and it's explained by a term called Voronoi diagram. Have anybody heard about this Voronoi diagram? It's a part of computational geometry. So the cells that we have in telephone towers, you see they are hexagonal kind of. You must have seen in the mobile towers that we have here, the cells are actually hexagonal kind of, and the motivation is taken from this concept of computational geometry. It's called a Voronoi diagram. Voronoi. What's the property of this? Property is that any 2 points in this entire space is divided by a perpendicular bisector. That's number one property. And okay. And the number two property is that any point you select, any point, all the points within this cell are its closest and not anything outside that cell. That means its closest points will lie within this cell itself. And that's why it says each cell C is the set of all points that are closest to a particular example xi. Say something which is here, this might not be closest to this. This rather, these points, this yellow boundary, they are closest to this particular. So this is a classic example of, you can say, the nearest neighbors. Right? So the decision boundary, again, we have a very ragged decision boundary here for 1NN, as Sir has just pointed out. How do we decide K? So we try to increase K, and the moment we say that, you can say a very smooth classifier. So, you know, the distribution of the data is such that here you see the red points have penetrated here, some red points have penetrated here, some green points have actually gone here. So it's very difficult to classify. Very difficult to classify. But the moment you have this kind of a classifier, where, say, suppose you have a certain class lying here and a certain class lying here, you know, class of points lying here, a class of points lying here. This is rather what I was discussing about the degree of smoothness, basically. It should be like this. When you give the model to an unknown sample, and eventually when you classify it, your classification, like the pictorial representation of your classifier should look like this rather than this. And this is only possible when you have a relatively larger K. But what's the difference? What's the problem when you have all the data points as K? That is also possible, right? I have n-1 NNN. From 1 NNN till KNN till n-1 NNN. Will suffer from the problem of over smoothing, basically. Over smoothing, that means it will be a near straight line kind of a thing, which is again not wanted. Right? So I'm discussing two extreme cases. One is your 1NN. What is 1NN? Just one person. I'm only accommodating one person. What is your n-1 NN? I'm accommodating everybody in my neighborhood. So I have just one circle. Just one circle and just one particular example how to train myself. There I will face problems of a linear, perfectly linear classifier, which will again lead to overfitting. Because when the unknown samples come, they will not see whether you are a linear classifier or not. They will come as per their own wish. And because you are a linear classifier, you might fail to classify them appropriately. That's the problem with n-1 NN. So ideally, it should be somewhere in between, 0 to n-1. Ideally, 5, 7, these are the, you can say, ideal numbers to talk about. Not an even number, but when you talk about the odd numbers, they are say around 5, 7, 9, 11, something like that. But not too large, not 25 or 29 and all of that, actually. Right? So, these are some of the, so whatever this slide will talk from here on, it will say involve quite a few equations. So, I've already given you the broader picture of how the things are. I hope people don't get bored by these equations and all of that. So the broad idea is that classify the things. It's not a regression problem, it's a classification problem. But if we think, what if this becomes a regression problem? Just think it in terms of your basic understanding. So what I have said is that I have a point, I have this neighborhood, and I am accommodating say certain number of points here, and the most dominating class becomes the class of this unknown point. That's what I've said. Because I'm classifying it actually. What if it becomes a regression problem? So in regression, as we have said here at the beginning of our session, that we don't allocate as such. Whatever comes as a real number, we stop it there itself. What is classification? Something will come as a real number, but then we'll apply one more formula to decide what is your bucket, what is your allocation. That's your classification problem. So if it's a regression problem, then what happens is you take this point, and these are its top k nearest neighbors. And suppose you find the mean of all these values of these top k nearest neighbors, mean of the coordinate values, for example, then it becomes a regression problem. That means call an unknown point. Now you are not going to say whether it's blue or green or red. You are just going to find some number or some property of this unknown number. That's when it becomes a regression problem. So every machine learning model can be treated both as a regression problem as well as a classification problem. For example, your logistic regression, you must have heard about it. I think anybody who has heard about logistic regression? Everybody. So it's a classification problem. It's very good. But the name is regression as such, but actually it's doing classification. How? So when your W1 x1 plus W2 x2 gets calculated, you are not keeping it here itself. When your sigmoid function is giving you a certain value between 0 to 1, I think sigmoid function, I think more or less, like those who are working in ML, you can understand 1 by 1 plus e to the power minus x. So when your sigmoid function gives you a certain value, you are not keeping it there itself. You are putting a threshold of 0.5 and say that if it crosses 0.5, you are belonging to a certain class. If it falls below 0.5, you are falling to a certain class. So you see how you are differentiating these two concepts of regression and classification. You keep it in between, it becomes a regression. You take it one step further and put a certain threshold and say that, look, if you are beyond that certain value, you are in my bucket. You are within that certain value, you are in his bucket. That's when it becomes a classification problem, but the name is regression. So every ML model can be treated as both as a classification as well as regression. So like I said, what if it becomes a regression problem? You take the neighbors, you find some property, say mean or variance or something, you find it, standard deviation. You come up to a certain number, then it becomes a regression problem. But we are not talking about regression, we are talking about the KNN classifier here. So the weighted nearest neighbor, instead of most frequent y in KNN, we predict. Instead of most frequent y in KNN, we predict this taking this argmax. So what is argmax? So argmax is a function which interestingly doesn't return the value of the function. Argmax is something which returns the argument basically. So suppose I have this, so I have say argmax, and similarly I have argmean also. So let me just now explain what is argmax. Say argmax w, and I have f of w. Fine, fair enough. Now, this is my function. Okay, this is my function, and this is one more kind of a, I mean, how to say it? It's acting on this function. It's a term which is acting on this function. There are two terms. One is argmean and argmax. Interestingly, I'm not taking any response from this function. What I'm taking is that I'm finding the value of w for which this function is maximum. And that value of w is actually returned as an output. Let's try to understand this. Similarly for argmean as well. So if you talk about any machine learning model, any training model, what effectively is a machine learning training? It's nothing but a function approximation. Those who are from the mathematics background. It's nothing but a function approximation. That means I take a certain loss function. I think you are aware about loss function. The MSE, the RMSEs, the MAs, the Hubel losses, the KL divergence, RBF, etc., etc. I take a certain loss function. What's my objective? Reduce the loss. Reduce the loss. How do I reduce the loss? Update the parameters. That means I am finding those parameters for which the loss is minimized. That's what we are doing. What do we do in linear regression? We have the mean square error, 1 by n summation of y observed minus y actual whole square. We expand it and then take the gradient. And weight prime is equal to weight minus learning rate into the gradient. So effectively what we are doing, we are trying to find this. We are trying to find these parameters due to which this loss is minimized. Is it not what we are trying to do? When we are, so everybody talks about training a model, training a model, training a model, training a model. But what is training a model? It's a function approximation at the end of the day. It's nothing like rocket science kind of. At the end of the day, it's just a basic mathematical function approximation. Which means that we take a certain loss function. So let us say LW in our case. We're trying to minimize it, but we are updating these parameters also. We are tweaking it. Let's see, let's change W to this, see whether it's coming down or not. Let's change W to this, see it's coming down or not. Let's change W to this, see it's coming down or not. And the moment it comes down, we say that, look, we have trained our model. And this W gets finally returned and it gets placed into that linear equation. Is it not what we are doing? Those who are working in the ML and DL field or AI field, I think you'll be able to understand this. So at the end of the day, what we are doing, we are trying to approximate a function to a certain thing, and in the process, whatever we learn. So that's the concept of learning basically. This learning, ML, machine learning, deep learning, reinforcement learning, supervised learning, all the learnings that we do, what are we learning at the end of the day? We are not learning any X or Y's. We are learning these coefficients. We are learning these parameters. These are parameters, not hyperparameters. Because when you talk about hyperparameters, we are going into that external validation kind of a thing. Fine? So this is what argmax is all about. Now what it says is that instead of just computing the distance, find the similarity between, say, any two pair of points. There are multiple ways to find the similarity. We adapt the similarity and say that which similarity or which combination gives the maximum. We take those as my nearest neighbors rather than plain Euclidean calculation, basically. So instance-based learning, the model is not learned a priori from the training set. So now I'll probably navigate these slides to move a bit fast. I think I've given you a broader picture of how things work, basically. So now I think it will be easier for you to understand, irrespective of the complexities involved. The model is not learned a priori from the training set to predict the test examples output. We store the training examples. We don't learn it, but we learn in course of our training. If the test instance is given, then try to predict its output from the stored data. Okay. So this is, I told to Professor Sahu, so he said that there is you can say the coding is not required as such, but just for the audience's benefit, I will show some snippets of code as such, the Python code, and it will be probably easier for us to understand that how you can say things are working in the background actually. So this is a 1NN case. In your training phase, we save the examples. I think you have a hands-on session, maybe a couple of days later on, probably. Get the test instance XQ, find the most similar training example, XJ, YJ. How do you find the most similar? One is do the simple Euclidean, find the top 5 nearest, top 7 nearest. Or the other is that you apply this formula and find the similarity, which is the highest. You get those as your closest points, basically. Predict Y is the output, YQ. This is your basic KNN. Save the examples in some suitable data structure, get the test instances, find the K most similar training examples. Now, this is where the catch lies. Like, I think everybody is able to understand now. How do you find the K most similar? Either go for simple distance computation or you use that argmax kind of a function, basically. In either ways, you are going to get those people or those data points who are somewhat similar to you. Now, see, this word similar is also very fuzzy, actually. Word similar doesn't mean that this Euclidean distance similarity is as obsolete as anything. And by obsolete means it's almost outdated. Like we work in, say tomorrow I'll be discussing say a couple of important clustering paradigms. We work in clustering algorithms which are not even looking at the distance-based similarity. It's so outdated. Like if I want to say that, see, I'm similar to say somebody sitting here, what's my logic behind saying this? Just because he's 5 feet away from me? Or just because you are 7 feet away from me, just because he is 3 feet away from me, is that the logic of similarity? This used to be the case maybe 20 years back. The way things are evolving, we don't compute distance-based similarity. And the answer is the reason we don't compute because of a problem called curse of dimensionality. I think people have heard about it. If not, please let me know. I'll explain it. Curse of dimensionality. It's a curse. Curse means shrap, basically. Curse of dimensionality. So what is curse of dimensionality? Curse of dimensionality means, suppose I say that I'm closer to him, and 20 years back I could have said that he is more similar to me via Euclidean distance or Manhattan's distance. And 20 years back I could have said that the colleagues who are sitting right towards the end, they are dissimilar to me. But is that a justification? How can I say that he is so dissimilar to me? We might be working in common field. We might have similar backgrounds. We might be speaking similar languages. We might be having similar heights. We might be from similar regions. But just that L2 distance or Euclidean distance says that that person is further from me, or say outside this campus, he is dissimilar and maybe he is similar. That used to make sense 20 years back, but not now. So all these things you are seeing, this, I mean, because it's a very foundational explanation, so I'll not go into the details. These are based on your Euclidean concept. These are your Euclidean spaces where your geometric distance calculation is successful. But basically we don't work in Euclidean spaces anymore. Your normal x1 minus x2 whole square plus y1 minus y2 whole square is flattened. That idea is debunked. Now the way of finding similarity is something very, very different and interesting. It's depending on the data distribution. How do you do it? Let me give a very small example. Talking about this KNN. Now, I have said as of now, in the course of my explanation, that I'm an unknown sample. I'm going to find my class. How do I do it? I put into a KNN classifier the dominating frequencies, the class level becomes my class. Fine. Now, I say that I have a 5 nearest neighbor concept. So 5 people are closer to me. Now, suppose I want to compare with him or say sir, and say that sir also has a 5 KNN kind of a thing. Sir's neighborhood and my neighborhood. There will be an overlap in neighborhood. That's going to happen. There will be an overlapping neighborhood. Now, doesn't it make sense to say that my neighborhood and sir's neighborhood, if there is a sufficient overlap, that means they are common to both of us? They are common to both of us. And if we are able to stay with these neighbors for a long period of time, that means they are close to us. We like these neighbors. We don't have any problems as such from these neighbors. Similarly, sir also doesn't have any problems as such with these neighbors. Now, can we not say that instead of computing this Euclidean distance, if we take the strength of this neighborhood and say that this is our similarity score between these two data points, does it make more sense or Euclidean distance make more sense? That's what is happening now, 20 years down the line. Now, if I want to find my similarity with somebody who is sitting at the back, I will say that this is my neighborhood. I have 15 people here. These 15 people are the common neighborhood of sir also towards the back. So my similarity strength will be 15 now, not our Euclidean distance. And that makes more sense than just computing the distance. Because if we compute the distance, he is dissimilar to me, right? Because he is 100 meters away from me. And if I just find the distance, he is the most similar to me because he is just probably 3 meters away from me. But you see, we don't have any common neighbor here. Are you getting this idea? This is called data dependent distribution. So your entire similarity concept is also very, very critical. It's not about distance anymore. Like, we have to explain this because I've come to this place and these are conventional techniques found years and years ago, but now the distances are not computed in terms of similarity. All the evolved clustering or machine learning mechanisms which are there. Gini index is an information gain, actually. It's about the decision tree that you are talking about. The decision tree, random forest, that kind of a thing. That is a bit different concept. There you have where the entropy kind of a thing is there. Where you have more information gain, you select that attribute, based on that attribute you do the division. Here similarity is very, very different. There are, I mean, to tell you the truth, there are around 25 metrics of similarity. I have just said one of them, the nearest neighbor. There are 25 to 30, more than that, different quotients of similarity, but not the Euclidean distance. It's a very, very obsolete concept, the Euclidean distance. Even the clustering algorithms that we do, that we simulate in our local server machines, mostly we code in C++, we don't use these similarities, this Euclidean. We code it in such a way such that the neighbors are actually picked, or we decide a certain function. We take a certain function, the function arguments are x1, x2, and certain parameters are there. Whatever the value it gets, that becomes our similarity, and the edge weight as well between these two data points. Gini index is more about your classification. You have the information gain based on the entropy. The attribute which is giving more information, you divide on basis of that. Basically. Right? I think I've been able to make it clear to a certain extent, the story about similarity. So the word similarity has a very strong context here. But here mostly, as I said, these are very foundational methods. So we'll talk about the Euclidean. So now I think it will be pretty easy for all of us sitting out here to understand. What is the task? Classification regression. Like I said, now I think it will be easier to, so if this slide is given later on, it will be very easy to understand what this slide says, because that's the way I convey to my students and peers as well. I take the crux concept, the concepts which are a bit more difficult, and share these slides to them, because just by navigating these slides, you don't understand what's happening. You know, just purely read out these slides and points after point and half an hour class is gone, basically. Just pick what the audience is finding out to be most difficult, or what the audience expects out of this presentation, basically. So we have said this here, the classification, the regression, predict the average, and I think that's what we said just a while ago, predict the majority class, you know, to put it very precisely. That's the mathematical description, nothing but whatever we have discussed in our time frame, basically. This is all what it is saying. List of training examples are there. What are training examples? The known examples. What are labeled data, by the way? What are labeled data? So we have a labeled data here because every data is associated with a class level. Okay. So tomorrow's session that we will be dealing with, it will be about unlabeled data. The data doesn't have classes as such. They are just raw data points. So inherently, you see, the subject is pretty complex. I mean, although we are discussing in a very layman's way and all of that, but inherently it gains on the complexity as we go with the complex ML models. So attributes of the instances, say A1x, A2x, and all of that. So what are the attributes, the dimensions? So like I said at the beginning of my lecture, every data point, don't treat it as a discrete entity. It's a vector. Every data point is a vector. Every data point. There is nothing called discrete in this ML space. You bring a certain data point X, just think that it's a multi-dimensional point, or it's a multi-attribute point, multi-feature point, right? The Euclidean distance between two instances, like I said, you know, because these are foundational models and for the sake of explanation, but the evolved research, what it says is that these kind of distances are no longer in function. I mean, you can, but if you want to publish in very, very highly reputed venues, you have to look at the, you know, similarity measures which are more evolved sort of. So this is the algorithm as such. Training algorithm, whatever we have discussed in first quite a few minutes, this is all what the code is saying, or the pseudo code rather. For each training sample, add the example to the list of training examples. Given a query instance xq to be classified, let x1 and xk till xk denote the k instances from training examples that are nearest to xq. How do we find the nearest? Either we have the max function, argmax function, or we do the conventional distance. And then we apply this, and then we go for the classification, basically. So this is all what we have discussed in our previous, like, you know, just a while back. So classification algorithm, given a query instance xq, let x1 to xk denote the k instances from, I think it's the same thing, that are nearest to q, and return we have this function will act as there, actually, where k is the size of your k nearest neighbor. This is a decision boundary, and this is a certain, you can say, live example. So we have to identify what is the, you can say, class of this student. His height is 157 cm perhaps, and weight is around 54 kilos. So we have medium, large, or small rather. So based on this, so you can say it's a 2D attribute data point, and based on this, its nearest neighbor will be computed. And if you see this red class is most dominating, so perhaps you have large is 2 and medium is 1. So large is the most dominating level, and this person will have the class as large. And that's all what we discussed in our beginning slide as well. Okay. So more on Euclidean distance, I will just skip this for the benefit of the audience. This is something we have already discussed. Small versus large K, I think sir asked this question. So everything we have discussed right at the front, right at the beginning. Rest of the slides is all about that we discussed. Maybe if you can like take these slides, it's everything that we put right at the beginning itself. So what is the problem with small k and what are the issues with large K or advantages with large K? Small k captures the fine structure of the problem space, but it can be very ragged. You see, this is not the classification that we want. You know, it's just finding out everything. It's playing a catch-up game rather. Whatever is there, it's trying to find it out. But when the unknown samples come, when the unknown data points come, you will suffer from the problem of overfitting. It cannot run after the points, right? It has to be generalized. At some point, it has to say that, look, this is the general boundary I draw. But if you keep on running after every new point that is coming, you will create a very, very rough classification boundary. That's the problem with small k, specifically with 1NN. With large K, I mean, if K is entire data set, n-1, you have a straight line. But with larger K, it's less sensitive to class noise. It allows a very smooth decision boundary as well for classification. Right. So that's all about KNN. And now we will start with the Bayesian learning, basically. KNN is just all about this. Okay. So we have around 1 hour's time, roughly 50 minutes. Yes. So Bayesian learning, or Bayesian learning rather, again it's one more ML classification model. The concepts remain the same. The concept of learning remains the same. What are we learning here? We are learning some coefficients, some weights, etc., etc. But a new term has now come up. We are not dealing with KNN anymore. We are talking about something different. And its motivation lies from the Bayes theorem, actually, Bayes theorem rather. So it's a probabilistic learning model. And the number of slides are pretty less here. Then we go to the dimensionality reduction, which is a bit complex. There I will devote more amount of time. This is something more with your, again, classification kind of a thing, either here or there. But what we do? So let us try to understand. So there are two things. It's a naive Bayes classifier. I think you have heard about it. Why do you call it naive? Why do you call it Bayes? Any idea? So I'll be able to discuss. Naive means, suppose, so just in your KNN, what I have said is that a single data point is a set of attributes. We don't deal with discrete data points anymore. Suppose if I talk about myself, say 3D. Kind of my x coordinate, my y coordinate, my z coordinate. If I talk about, say, any of you sitting out here, x coordinate, y coordinate, z coordinate. So you are a 3D space, basically. Now, why it's called naive? Because in these 3 dimensions, every dimension, the influence it is giving on the final classification is independent of the influence that the other dimension is giving on the classification. Naive. What is the meaning of naive? Novice. No idea. What's the meaning of naive? What's the literal English meaning of naive? Novice, no idea, innocent, doesn't know anything, less influential. That's the general meaning of naive. So let us dissect these two terms, naive and Bayes. Bayes comes from the Bayes theorem of probability. And naive comes from this concept. Suppose I take a certain data point, I have, say, n number of attributes. Every attribute, the influence that it has on the final classification is independent of the influence that the other attributes has on the classification. That means it's naive, it's unknown of the influence that the others are giving. Similarly, others are also unknown of the influence that it is giving. That's why it's called naive. It's independent kind of, naive. And why it's called Bayes? Because the entire concept comes from the Bayes theorem of probability. That means if you have 2 events, A and B, then there are terms called evidence, a priori, likelihood, and posterior. Right? So let us see. So Bayesian learning is based on the probability model. Given a data D, objective is to find which hypothesis H provides maximum posterior probability for the given data D. Now, if you look at this line, so this entire concept of naive Bayes classifier can be summed up with one single equation or two equations at max. I'll try to wrap it up within 20 minutes because we have to go to dimensional tree reduction, which will take a lot of time. It's pretty complex, basically. So this is more or less like, not like KNN, but its objective is just like KNN. KNN also does classification regression. This primarily does classification. If you want to put it as just a real number answer, it can become a regressor problem as well. Just that it is using probability, and that used more of a geometry sort of a thing, the Euclidean distances and all of those things, basically. So let us focus on this line. Given a data D, objective is to find which hypothesis. So what is a hypothesis? It's a claim, kind of. It's a claim. Now, suppose the claim is that, say for example, this university will come in top 50 in next 3 years time from now, nationally or globally, for example. It's a claim. It's H, the hypothesis. What's the data? The entire staff, the entire crew, the entire community of this place is the data. Now, what is the probability that it will come within this top 50 or top 20 rather? What is the probability? So a certain value will be there between 0 to 1. But for that, you have to find out individual probabilities as well. Say, now if I say there are two events, A and B, the conditional probability of A given B is it visible to everybody? Fine, right? Okay. What is the conditional probability? So let us come from the conditional probability basically. It's the sample space is now reduced. That means probability of an event A given that B has happened. We are not talking about the universal sample space, just a reduced sample space. That means given that B has occurred, we are finding with respect to B what is the chance of happening of A. So this is nothing but P A intersection B by P of B. Fine, fair enough. So let us put it as equation 1. Okay. Now, if I look at the other way, the other case, P of B given A, given that event A has already happened. So these are, see, two different things. One is that what is the probability that your hypothesis of coming within top 50? But for that, you got to know what is the probability that this data set will exist. Tomorrow, a new set of staff members might come up, right? A lot of people might get some better opportunities or relocate to a different place. You have to find what is that this 1000 or 1500 staffs who are there, they are there. Their probability you have to find out. Before you find out the other probability, that hypothesis that it will come in top 50. So both those things are required. The probability that it will come in top 50, given that this set of employees will be there. For that, you have to find out what is the probability that this set of employees will be there, given that you go in top 50. These are two different things coming from two different directions, both the things you need. And they're not having an influence to the other. Tomorrow the staff members might change as well. That will hamper your claim as well, your hypothesis as well. Right, that's what Bayes' theorem says. So what is this? This is nothing but, so your numerator perhaps remains the same, and your denominator becomes P of A, right? So your reduced sample space is now A. Okay. So let it be equation 2. Fine. I think it's visible to colleagues at the back. Right. Now, what do you do? P A given B into P of B equal to PB given A into P of A. Okay. And from here, we have the bias theorem, basically. So if we want to find this hypothesis that the university will come within top 50 in 3 years' time from now on, suppose this is my hypothesis and this is my employee structure, my final equation will be this entire thing, right? So now the game starts, right? Fine, we stop here now. Now see what happens. This, I'm not writing this is the numerator basically. This term is called the evidence. Evidence, E-V-I-D-E-N-C, evidence. This term is called a priori. A priori. What is a priori? Probability that your claim of hypothesis of going into top 15 rankings before any evidence happened. Before any evidence happened. You had no evidence previously, just you threw the claim that I am going to go in top 50. What is the probability of that? That is actually taken care of by this. This is known as a priori, and this is known as the likelihood. Likelihood. So there are three things. Your evidence, your a priori, that means probability of a certain thing happening before any evidence happened, before you got any evidence, and this is your likelihood, and this is your posterior. Posterior probability. That means given that you are claiming that you will go to top 50, given that you have this employee structure. So here the ML model or the machine learning model is acting as a classifier that under two circumstances. So if it's a binary classifier, class red and class green, individually I'll calculate which has more probability. Either it's going to rain tomorrow or it's not going to rain tomorrow based on your features of this day. Say cloudy, humidity, temperature, pressure, etc., dew point, etc. I throw this, I put this here, then I will find two different probabilities based on the training data. Whichever probability, so whichever the posterior probability will be more, that will decide whether it's going to rain tomorrow or it's not going to rain tomorrow. That will decide whether you're going to come to top 50 with this employee structure or you are not going to come to top 50 in this employee structure. So suppose say 5 more employees have added up. Then your evidence also changes. Right? So this means, what this means is that the naive word, this is a bias theorem. This is not yet naive bias classifier. This is a bias theorem. Why this naive bias? Because, why this naive bias? Because of this term. Because of this term. Now, this term, by and large, it will remain constant. By and large, if you don't have any updatation of the employees, by and large, it will remain constant. But this term means, if it's a multi-dimensional attribute, like I said, every data point we come with a multi-dimensional attribute. Every attribute that exerts influence here is independent of the influence that is exerted by another attribute. So what happens is, I'm trying to be as simple as possible, but things are not that simple. So what happens is, this numerator is nothing but a product of individual features. Okay. Given that this B is now, say, this B is now composed of, say, B1, B2, ... Bn. Right. So this will now become P of Bi given A into P of A. Into P of A divided by this evidence, which is again a total probability. That means it is nothing but summation of P B given AI into P of AI. Please pardon the handwriting, I'm using the mouse pad. So just try to understand, there's a lot of irregularities will be there. I'll come to the equation, just let me complete it. This is the entire naive Bayes classifier. There are very complex maths in the upcoming slides. I will not go into it. Just want to make that everybody understands what it is all about. Yeah. So till here it was a Bayes theorem. This is your Bayes classifier, naive Bayes classifier. And its root is based on your Bayes. This is a Bayes theorem of probability, basically. What is the probability of a certain hypothesis happening given that certain thing is already there? What is the probability that certain thing is there given that this hypothesis is there? This domain is all about Bayes theorem. It's a classic probability. But where is the machine learning part of it? You must be wondering where is the classification? The classification is that this posterior probability we are now calculating based on this formula. And why it is called naive? Because if you see this term, this entire thing, so it will be P of B1 given A into P of B2 given A into P of B3 given A into P of ... P of Bn given A into P of A. So this into, each of these terms are not exerting any influence on the other term. I hope I've been able to make things clear. Each of these terms are not exerting any influence on the other term. That's when it's called naive. That is why it's called naive. Because if it was not naive, I could not have written in this way. If it was not naive, I could not have written in this way. Because here I am taking the liberty of this innocence and I am saying that now multiply all of them. Because they're not casting any influence on each other. That means if it's a multidimensional attribute, I can say P of B1 given A into P of B2 given A into P of B3 given A ... into P of Bn given A. They are all multiplied. Because it's not creating any problems as such. That's the naive. And this denominator is the total probability. This evidence can be expressed as sum of the individual probabilities. So P of B is nothing but P of B given AI, given that AI is also like there are multiple components are there. P of B given AI into P of AI. So I goes from 1 to n. I will go from 1 to n. That means P of B given A1 into P of A1 plus P of B given A2 into P of A2 plus P of B given A3 into P of A3, and this is your denominator. So whatever computation is coming here, that is now returned here. Now suppose if it's a rainy day, you will have a different value here. If it's a non-rainy day, you will have a different value here. Whichever value is more, that will be tomorrow's weather prediction. If it's a rainy day, I'll come in the next slides. If it's a rainy day, your a priori will have a different value. If it's a not rainy day, if it's a sunny day, your a priori will have different value. Then this entire fraction will have different values. Out of these two different values, whichever value is more, tomorrow will be that probability of happening is more. Either it will be rainy and say that, okay, with this data that I have, our claim that tomorrow it will be a rainy day. Got this point? Now, these things can be more understood. Yeah. So P is the initial probability that hypothesis H holds before we have observed the training data. P of H is called the probability of H, prior probability of H. The probability of observing D given that hypothesis, these are very conventional, just definition itself. And PD, the prior probability that training data D will be observed actually. Now what is the maximum posterior? It's nothing but argmax. So again we have argmax. Why argmax? What are we doing here? Our objective is to find which is the maximum posterior. Please don't confuse with the loss function. Loss function was to minimize the loss function. So there arg min was acting. Here it's argmax. Why argmax? Because our goal is to find out based on this data which is maximum. Either rainy day computation is maximum by naive Bayes classifier or sunny day computation is maximum due to naive Bayes classifier. Whichever is maximum, I will pick that H. And say that, okay, tomorrow's, if rain, based on this formula, if I say that your rainy day classification value is having more, this fraction will have more value basically. Then I say tomorrow my chance of rain is more. So it will be a rainy day. But again, I cannot say that it will be a rainy, I can just say that the probability of rain will be more. That's what. I cannot exactly say that whether it will exactly rain or not, or it will be exactly sunny or not. These are all probabilistic models basically. I can say 70%, 75% chance of rain will be there. Now, when I put my sunny day, so I will get this data from my training data set. If I put my sunny day data here, again this fraction will give me some value. And if I say that 25% chance that it will be sunny day, 75% chance that it will be rainy day, I can say that, okay, tomorrow will be a rainy day, basically. That's the fundamental concept of naive Bayes. Okay. So the argmax, obviously, the one which gives me maximum probability, that will be your, you can say, the final classification. And then we have the maximum likelihood hypothesis. In some cases, we assume that before learning any data, the probabilities of all the H are same. These are again the typical cases. But our goal is to maximize the a priori probability, basically, which is again we are taking the argmax. PD given H is often called the likelihood, and these are the terms that we have already discussed in the previous thing, in the previous concept with A and B events. This is a classic example. I think most of the books will suggest this example, basically. So the patient has, so let us take a certain disease here. The patient has a particular form, and the patient does not have a certain disease. So it's not specific to the disease that is shown here. It can be any chronic disease, any ailment rather, any problem. Two lab tests, they come out to be as positive or negative. The prior knowledge is that over the entire population, people, only 8% have some form of a certain disease. Okay, let's not specify a certain disease here. It can be any disease, for example. And then we have, in case of the actual disease, the lab test returns a correct positive result in only 98% of cases. If there is no disease as such, the lab test returns a correct negative result in 97% cases. Now, for the new patient, your Bayes classifier will decide which probability is more. Either the disease probability is more, or not having the disease probability is more. So these are the you can say general applications of your naive Bayes. The thing is that in your KNN we use the geometrical concept, the distances and all of that, the dominating classes for doing the classification. Here we are just using the probabilities. We have the events, we have the training data, and then we find out the individual components. So just remember this formula each and every time. You need to find out these values basically. Once these values are found, some value you will get here for a certain class, then again change it to another class value, you will get some value, whichever is more, that is your classification. So based on a rainy day data or based on a certain disease data, you will get some probability. Based on a non-disease data, you will get some probability. Whichever is more for the unknown sample, that will be his class, actually. Okay. So that's all about it. And yeah, this is a you can say live example. Playing tennis or not playing tennis. If you can say that your target is to decide that given the weather conditions of today, either it's suitable to play tennis or it's not suitable to play tennis. Now again put in that this naive Bayes classifier. So what are the you can say weather conditions? Outlook, temperature, humidity and wind. Okay, these are the parameters we are taking, and for each of them we are having this value. Say sunny. Say for example, if you see how many are sunny, say 1, 2, 3, 4, 5 basically. So your no cases are, I think totally you have 9 cases basically. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. So yes and sunny. So yes is 9. Out of these 9, how many are sunny? So out of the 9 yes play tennis cases, how many are sunny day? So you can have, say, out of these all the yes cases, you can probably see, so this is yes, and maybe one more we have here. And this is yes. So that's why it's 2 by 9. Out of the 5 no cases, again, how many are sunny? So out of these 5 no cases, 1, 2, 3, 4, and 5, how many are sunny? So perhaps we'll have 3 sunny and no cases. 1, 2, and I think, okay, you have 2 rather, yeah, only 2. So it's 2 by 9. Oh, 3 by 9 rather. Okay, so we have 1, 2, and I think this, yeah, 3 by 9. 3 by 5 rather. Yes, there are, you can say 5 no, right? 1, 2, 3. Pardon? No, yeah, this 3 by 5, I'm telling. 5 no cases are there, right? No play tennis. Yes, number of times you play tennis is yes, it's 9. Number of times you don't play tennis is, number of days you don't play tennis is 5. Out of this 5, 3 days are sunny and outlook, under the outlook condition. Number of days you play tennis is 9. Out of this, the number of days which are sunny days under the outlook condition is 2. That's why it's 2 by 9. So totally you have 14 samples, right? So in this way, you find all the values here, and then you decide that what are your individual values. You go to this formula once again. Go to this formula, we have to find out what are the individual values here. Then for sunny day, I will find a certain probability. For rainy day, I will find a certain probability. And what is this naive Bayes factor? This, actually. Why it is called naive? Because these attributes, individually, they don't cast any influence on the other attribute. So these values, whenever we are multiplying, this numerator, whenever we are multiplying pi of P AI, say BI given A, B1 given A into B2 given A into B3 given A, it's these values, these individual values. And they are actually not casting an influence on the final impact. That's why they are multiplied grossly. And we require these individual values. Okay. So as you can see here, it's finally the expansion of this. So due to lack of time, possibly we won't be able to go into the details, but finally it's all about this one, this. That's the crux of the naive Bayes, actually. Two independent claims are there, two events are there basically. If you need to find a probability of one given the other has happened, you need the values of these few entities which are existing, actually. So I hope somehow like things have been, so due to lack of time, I will not go about the risk minimization. This goes into like some complex maths and all of that. So can we come to the dimensionality reduction, the final topic? The classifier is just about this. The Bayes classifier is just about this. So two claims or two events will be there. Just have that formula. For one class, put the values in that formula, find a certain value. For the other class, again find the certain value. Whichever is maximum, the new sample or the new feature vector will go to that class, actually. So now we come to dimensionality reduction. And yeah, I wish I had more time here because this is a bit different and a bit complex as well as compared to the other two. But I'll try to wrap it up within half an hour time. So like I said at the beginning, there is a term called curse of dimensionality that I used. If you remember the term called curse. So what is the curse of dimensionality? Now, the question is that why are we reducing the dimensions in the first of all? That means bigger dimensions has some problems, or else why would you go for reduction? We can say that yes, we can plot 40 dimensional value as well, 50 dimensional, 70 dimensional, etc., etc. But we are not doing that. We are saying that no, we want to reduce. The one reason is the plotting, the visualization. Beyond 3D, we won't be able to visualize. And the other reason is this curse of dimensionality. So let us try to understand why are we even studying this field actually. So in your school days, you must have seen there is a concept of density, which is nothing but mass per unit volume, right? I think everybody remembers from your school days. This means what? Density is inversely proportional to volume, right? Now, what happens is, let us say these are my data points. Again, before navigating through the slides grossly, let me try to give you the broader picture of what this is all about. It will be easier for you to understand. When I have a high dimensional space, say these are my data points, and every data point X belongs to RD. That means X has multiple number of features. The simple way to convey is X has multiple number of features. Fine. Now the target of this slide is reduce or trim these features, perhaps to 3. Because only if it comes to 3, we can plot it. If it's more than 3, we won't be able to plot it. That's one of the reasons. The other reason is that problems with this formula. So let us try to understand what are the problems here. Now, as I have said, this density is inversely proportional to volume. That means as the volume of this space increases, my density decreases. Fair enough? As my density increases, the volume of the space is thought to be decreased. Now just try to understand this. Suppose there are 20 people in this room. I bring 200 more people here. That means what? I make it heavily compact. Density increases. But has the size of the room increased? No. Its volume is more or less same. Suppose I make it even dense. I make 2000 people around me. Just say hypothetically imagine in a very compact space. Very, very compact. It's just like you can say maybe of size of the marble basically. Very compact. That means its volume now decreases. Now if I break this, what happens? It's becoming sparse. Now its volume is increasing, but your density has decreased. So in high dimensional space, what happens is when we increase the number of features or when we increase the number of attributes or dimensions, there is a property that the volume gets increased because it spreads out. Its volume gets increased. And if its volume gets increased due to this equation, its density will get decreased. Agree? Now see what's the problem is. If the density gets decreased, will you be able to find clusters or groups? Answer is no. If I say how many clusters or groups are there, probably one table is a certain cluster. Cluster of 4 points, cluster of 2 points, cluster of 4 to 5 people, cluster of 6 to 7 people. But imagine your volume has increased drastically. Right? Your volume has increased drastically. That means what has happened? Your density has reduced. Your density has reduced means your sparsity has increased. You are becoming more sparse now. You are not compact anymore. You are more sparse. More the sparsity, your cluster formation capability decreases. This is the layman's concept that I am giving without going into the maths. Because if I go into the maths, it might be a bit more overwhelming or difficult. Because you have audience from say different fields. This is the basic layman's concept that I am supposed to explain. Just imagine, your volume increases, your density decreases. Density decreases means what? The crowd decreases. The condensation decreases. That means you are now spread out. If you are spread out, your ability to find clusters will get reduced. What tomorrow we'll discuss in our tomorrow's session. That means your cluster formation capability has gone. But are you really that bad? So what, you are spread out? You can form clusters there also, no? You can form clusters there also. You can form clusters there also. This is known as the cars. That irrespective of this, irrespective of possessing some capability, you are actually deemed as your clustering capability will, it will gradually tend to decrease. It's not that all of a sudden you will not be able to find some clusters, but in general you will not be able to pick up those patterns from the data set because it is spread out now. On the contrary, if I say that your density is very strong, you are highly crowded, I can very easily say that, look, this is a cluster. Because in front of my eyes, there will be 1,000 people. I can say that, look, this is a group of 1,000 people. So the fundamental concept is that with high dimensions, your volume increases, your density decreases, and your ability to find patterns from the data set decreases, goes away. That means your clustering capability goes away. That is known as the problem with dimensionality, high dimensions. Am I clear? Am I clear with the issue? First, try to understand the problem first. This is the problem. So if this is the problem, how I am going to solve this problem? Like, this slide is inherently complex. I won't discuss each and everything, but this is what this slide actually talks about. As we have been doing in our other two concepts in KNN and knife bias as well. Now, how to solve this problem basically? I have to cut the dimensions. Because larger number of dimensions are creating problems, right? More the number of dimensions, more the volume, less the density, no clusters. So if I cut the dimensions, my volume will tend to decrease. And as my volume tends to decrease, my density will gradually keep on increasing. And as my density keeps on increasing, my ability to again extract clusters from the data space will increase. That means I'll now be able to detect the patterns. Am I clear, everybody? If I reduce the number of dimensions, that means now my sparsity will decrease. Sparsity decreases means my crowding increases, my density increases. That means भीड़ जो है, जो crowd है, that increases. And as my crowd increases, the condensation increases and my ability to find clusters increase. That's the motivation of reducing the dimensions. That's why the problem is dimensionality reduction. Is it clear, everybody? Right. So let's move ahead now. It can be divided into feature selection and feature extraction. So what are features? These dimensions are nothing but the features. The feature projection or feature extraction transforms the data into high dimensional space, in the high dimensional space to a fewer dimensions. Now, the thing is that, I'm not aware about it. Do you have any background of linear algebra or vector matrices? It actually requires that. So I'll try to simplify it as much as possible. So please try to understand, because or else it will be very difficult to understand. Now, there are multiple techniques to reduce the dimensions. One of the basic fundamental techniques is principal component analysis, or PCA. Right. So there are others as well. SVD is there, and you have, I think, TSNE, stochastic neighborhood embedding, those things are there. So let us try to understand what this PCA is all about. So suppose we have this high dimensional data points. Now these data points that I'm drawing, they are high dimensional. I'll wrap it up after this explanation. I'll wrap it up basically, because the rest of the slides are more about the explanation. Okay. So these all are X belongs to RD. What does this mean? RD, it's a D-dimensional space, and D is very large. So for us, D is equal to 3. For us, for human beings, D is equal to 3. In general, D is sufficiently large. I think 30, 40, 50, 100. It's a high dimensional space. Now what happens is, let us draw a table here. Okay. This is called as the embedding table. And these are my data points. Say this is your P1, P2, P3, P4, etc., till Pn. So everything that this entire slide will talk, I'll try to give in this particular explanation itself. Okay. So we have here P1, P2, ... Pn. Right. I hope it's visible, everybody. Right. And what is your horizontal axis? This is nothing but your dimensional attributes. So this stretches from 1 to D. So first feature, second feature, third feature, and this is your dth feature. Fine. So suppose this is the story of P1, and these are all real number encoded actually. 2.1, 3.1, minus 1.3, anything between minus infinity to plus infinity. Again for P2. First dimension value, second dimension value, third dimension value, stretches, and dth dimension value. And again the nth data point, the first dimension value, the second dimension value, the third, and so on. And we have the dth dimension value. So effectively you have constructed a matrix. So the size of this matrix is n cross D. Agree, everybody? N cross D. N number of data points and D features per data point. What is our job? To reduce D. Because D is creating problems, right? More the D, more the sparsity, less the condensation, no clusters. Our job is to reduce D ideally to a certain value, say k. In future, we'll see what happens. So now how to reduce D? What we do is that if we look at any two data points, and their individual dimensional values, don't they signify a random variable in statistical concept? What is a random variable in statistical concept? Say x is a random variable, it takes values say x1, x2, x3, x4, xn. I think most of you are aware of that. Suppose you take another random variable which is y, y1, y2, y3, dot, 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 yn. Now, if we try to visualize any pair of data points from this data space, say P1 and P2. Say P1 and P2, or say any Pi and Pj, for example, any Pi and Pj, where Pi or I not equal to j and Pi and Pj belong to this data space. Now, what are its individual dimensional values? This, that means this thing and this thing, right? Am I clear, everybody? So straight away I'm putting the dimensional values here, say 1 to D, and here also straight away I'm putting the dimensional values, say 1 to D. Fine, fair enough. Now, if I just try to understand, this is a very critical part of this entire explanation. Just try to understand this. If I take, see, these are my data points from the data space, any two data points. If I try to take any two data points, not only P1, P2, P3, P5, P99, P100, P75, P50, any Pi, Pj, where I not equal to j, non-overlapping points, and I put its individual dimensional values and treat them as separate random variables. And these are my values of the variables. Are you able to understand, everybody? I take a point Pi, whatever its individual, so suppose Pi is here and Pj is here, it has its individual dimensional attribute values, it has its individual d-dimensional attribute values, I put it here, right? So what I'm doing is, this is D, and suppose this is your Pi, and say, suppose this is your Pj. Right. So now, if I find the covariance between these two values, covariance, how they are varying mutually. What is the formula for covariance? 1 by n minus 1 summation of xi minus x bar into yi minus y bar. Got this? 1 by n minus 1 summation of xi minus x bar into yi minus y bar. So, if what I do is that, what is your x bar? X bar can be, so suppose this is your x variable, this is your y variable. And what I do is, I find the mean of all these values. That can be x bar. I find the mean of all these values. That can be y bar. Now, this value minus mean of this into this value minus mean of this into xi minus x bar, right? So this value in this value minus mean of this into this value minus mean of this, plus this value into minus mean of this into this value minus mean of this, plus this value minus mean of this into this value minus mean of this. So x minus x bar into y minus y bar plus x2 minus x bar into y2 minus y bar plus x3 minus x bar into y3 minus y bar, and we are finding the covariance between Pi and Pj. Till now it's clear or not? Fine, fair enough. Now see what we do. We construct another matrix. So if I can take help of this software, just don't mind, this is what we use in our classroom, at least I use. I construct a matrix, and this is known as the covariance matrix. Very good. It's known as the covariance matrix. So let us say this as COVXY. COVXY, and every cell value, so suppose this I comma j, suppose this is I comma j, this is nothing but, this cell value is nothing but covariance of pi comma pj. Fine? Fine? So suppose say this is 2, 3. So suppose this is cell 2, 3. Okay? Suppose for example, this is 2 in the vertical and 3 in the horizontal. So if I look at this, it's about second point and third point. Are you able to get something? It's about second point and third point. Now, second point's d dimensions I will bring here, third point's d dimension I will bring it here. Then what I will do, I will use this formula 1 by n summation of xi minus x bar into yi minus 1 by n minus 1 into yi minus y bar. Okay, and what are my xi's? These are my xi's. These are my xi's. And these are my yi's. What is my x bar? Mean of all these dimensional values is my x bar. Mean of all these dimensional values is my y bar. So nothing is unknown here actually. Everything is known. Everything is known. These xi's are nothing but this. These yi's are nothing but this. What is y bar? Mean of all this, mean of all this. X bar and y bar is 2 fixed values. So every time this minus x bar into this minus y bar plus this minus x bar into this minus y bar plus this. So this is your covariance of pi pj, and this is what you actually put here. So for all these cells, for every cell, some I and j will be there, say P1, P5, P7, P9, P9, P10, P99, P100, PK plus 1. Any cell you pick, you find the covariance. That means you pick the second point from the data set, pick the third point from the data set, find out its d dimensions, find the covariance between both, put it here. Is it clear, everybody? Am I able to make sense? This is known as your covariance matrix. That is part 1. Now, what happens is, let us say this covariance matrix is of dimension n cross n. N cross n. N elements in the vertical, n elements in the horizontal, it's n cross n. Now, are you familiar with eigenvalues, eigenvectors? Anybody? Can you please, if you don't mind me, how many? Raise your hand. How many? Eigenvalues, eigenvectors. Okay, only 2. Okay, fine. So I'll try to make you understand in last 10 minutes of my talk. Again, it will be a very layman's description. It's a big history of eigenvalues and eigenvectors. So effectively now we are dealing in vector spaces. These are all vectors. Pi is a vector, Pj is, they are no longer data items anymore, they are vectors now. Basically, we are going into core ML. Now, eigenvectors means this A is now treated as a transformational matrix. Pardon me if I'm using slightly complex terms, but I have to use for making you understand. In a d-dimensional space, this is a certain transformation matrix. That means it actually represents a mapping from vector u to vector v. So consider there is a function where your input is vector u, your output is also a vector. That means both domain and your codomain are both vectors. Now this mapping is represented by a transformational matrix. This mapping. That means if I say that who is the monitor of this class, who is the captain of this class, or who is the HOD or principal of this entire department, a certain individual. So you can say this entire department will be represented by that certain individual. So you can say a certain mapping, there is a certain mapping behind this. What is that mapping? It's the covariance mapping. This entire mapping is represented by this covariance matrix. And suppose say let A be that covariance matrix. It is also known as a transformational matrix. So what is eigenvalue here? And what is eigenvector? Eigenvector means a vector which points towards the direction of that matrix. If you're not aware about the physical meaning, that's the physical meaning. Eigenvector means a vector which points towards that matrix. And eigenvalue means the scale. What is the length of that vector? Again, those who know about eigenvectors are not unique. There are multiple eigenvalues, there are multiple eigenvectors. That means multiple pointers to this transformational matrix, basically. That's the geometrical meaning. So in this space, I'll come to how the dimensions is reduced. It's a long story. I'll cut it short. In this space, there are multiple pointers. And each of these pointers are nothing but your eigenvectors. And how these eigenvectors are found out? By a certain equation called the eigenequation, where A is your transformation matrix, lambda is a certain scalar entity, I is your identity matrix, and this is equal to 0, and your determinant is actually equal to 0, not that this is equal to 0. So once you simplify it, you will get a scalar equation, be it quadratic, cubic, or n-root polynomial equation, and you have this on the other side. When you solve this equation, the roots of this equation are your eigenvalues. Fine, fair enough. That means this is eigenequation. Now, if I talk about eigenequation, it will consume another half an hour, so I will not do it basically. Just know that this is a certain equation called the eigenequation. Somewhere it is there. Okay. Coming from this transformation matrix. Once you solve this eigenequation, that means the determinant, so this is a vector entity, this is a matrix minus a identity matrix multiplied by the scalar. This is an entire thing is a matrix. If you take the determinant and equate it to 0, you will get a simple quadratic equation or a cubic equation or a n-root polynomial which equates to 0. Now once you solve this equation, you will get, say, k number of real eigenvalues. There can be complex imaginary eigenvalues also. But these are my real eigenvalues. Now these eigenvalues are nothing but length of these eigenvectors. So if you put these eigenvalues back here, you will get certain solutions of the system of linear equations. They come from the system of linear equations basically. So once you put this eigenvector back into this, so actually the equation looks like this. A minus lambda I. Actually, I mean, it's very difficult to understand this if you don't have the prerequisite of probability and vector algebra. All of a sudden it strikes like anything. So that's why what we do is that our any machine learning course is preceded by 1 semester of maths for machine learning, basically. In most of the good institutes, you have we don't learn any ML as such, straight away only maths for ML. And then when they are getting fully prepared, then we throw them the ML algorithms, basically. Okay. So A minus lambda I into X equal to 0. This X is nothing but the solution to this equation. It's the X vector, solution to this equation. So once we find the solution to this polynomial, if we put it here each and every time, you will get certain vectors as my solutions, and these vectors are nothing but the eigenvectors or pointers to these transformation matrices. Say K. Now what we do, this is the last concept and probably the most important. As we find these eigenvalues, rather than going through the slides, I think this is probably helping a bit more. As we find these eigenvalues, we sort them in increasing order of their magnitude. This is the last concept. I mean, that's where the dimension is getting reduced. As we find these eigenvalues, we sort them in increasing order of magnitude. More the eigenvalue, more is the length of this vector. Agree? More the value of the eigenvalue, more is the length of this vector. That means the geometrical meaning is higher the eigenvalue, it is capturing more variance in a particular dimension. I am repeating it once again, very critical. Higher the magnitude of my eigenvalue, say lambda k, it is capturing more variance in a particular direction. That means the data sensitivity is very high. In Hindi, if you call it halchal. Sensitivity is very high. Data is, entropy is very high, randomness is very high. That means more information gain is there. Try to understand. More the value of my eigenvalue, it is scaling up the eigenvector, that's all right, but it is pointing in that direction where my sensitivity is very high. That means variance of the data is very high. That means if I take that as one of my primary components, I am going to gain more information, and that becomes my first principal component. Out of 40 dimensions, which dimension I am going to choose? If I am going to reduce 40 dimensions to 3 dimensions, do you really believe I am picking 3 out of 40? The answer is a big no. I am going to pick that direction where I find most sensitivity of the data, where the variance is very, very high. That means the eigenvalue corresponding to a certain eigenvector, this is pointing to this transformation matrix, all right, but it is pointing to that direction where the data sensitivity is highest at its peak. And we decide that if we give that as my first principal component or my first dimension, that will do more justice to a reference frame. For example, if I am going to reduce this 3-dimension to a 2-dimension space, simple reduction, I'll actually find out, do this entire covariance matrix, I'll actually find out that eigenvector corresponding to the highest eigenvalue, because that is capturing more variance. I am having more sensitivity maybe towards the end. That will be my first principal component. Is that fine? Now, what will be my second highest principal component? This will corresponding to a certain eigenvector, which is pointing to a certain direction where sensitivity is there, but it's slightly less than what it is there at the highest one. If I go lesser than this, so as we go less, your sensitivity capturing ability is decreasing. That means you are getting more into a stable zone. You are having less entropy, less sensitivity, less information. Just try to understand this. Less sensitivity means less information. More sensitivity means more information. And the direction where my sensitivity is more, my importance of the direction is also very high. Yes or no? The direction where my sensitivity is less, data is very stable, my importance of the direction or dimension is also less. And that's why these are my principal components. How do you decide which is principal? It's not 3 out of 40. I have 100-dimensional data space. How I am going to pick which 3 dimensions I am going to pick? I have to reduce the dimensions, right? If I don't reduce, I have the problems of curse of dimensionality, which I discussed few minutes ago. How are you going to reduce it? It's constructing this covariance matrix, framing this eigenequation. This is a discussion for another day maybe. Framing this eigenequation, find the root of this polynomial, find these eigenvalues, find the corresponding eigenvectors. Now, the vector which is corresponding to the highest eigenvalue, that is your first principal component, the most important dimension. The vector which is corresponding to second highest, because they are already sorted in increasing order, lambda k minus 1, whatever will come vk minus 1, that will be your second dimension. Say for example, if I pick this is your say first important dimension, this is say your second important dimension, and this is say your third important dimension. So this is, for example, this is say Vk, this is say Vk minus 1, and this is say Vk minus 2. And we don't go further, because as we go here, we are actually getting into a less sensitive zone. These are less important dimensions. And that's why these are kind of rejected. So basically it becomes a very reduced number of dimensions. It's effectively becoming a 3D or 4D space from a D-dimensional feature. And that's what the fundamental component of principal component or PCA is actually. So I'll stop here. There are quite a few you can say dimensional reduction techniques are there. We reduce from n cross d to n cross k as well. But this is the fundamental technique, and you just need to sort it. Whatever the eigenvectors that you find, take the top 2 or 3, they are your prime dimensions, because you find more variance in that. Your information is very high there. Fine. So thanks for having me. I'm a bit exhausted now, so thank you.
Thank you so much, sir, for this wonderful session.